Okay, here's a video on one of the hypothesis testing problems from the online homework. I'll do all the steps the same way we did in class by hand, but I'll also point out that the StatCrunch has a little calculator that will do some of the steps for us, and I'll show you that at the end of the video. So one of the most important parts is to identify what it is exactly that we're testing, and to try to say it carefully in words. So remember the difference between a variable and a parameter. That's what this first question is getting at. The word variable here and the word parameter here. So a variable, remember, is just the question that we would ask on a survey. So especially with a measurement that we're taking from a survey, the variable is just the question itself. And then the parameter is the measurement that we believe, the measurement on that variable we believe is true in the entire population. The thing that we don't know for sure, the thing that we're going to test a hypothesis about. So the variable would be the question about whether garlic or placebo is more effective. And again, the variable is coming from a question that's being answered. And the population parameter is just going to be the proportion of the population that either from garlic is more effective or the placebo is more effective. This question is a little bit weird because they give you both those options, and they both are actually okay. There is a tendency to think of, if we can, to think of P as being the proportion of success. And so in a clinical trial, you would think that the active thing you're doing, the garlic, is success for you. And so it makes more sense for P to be this value, so for this answer to be true over here. So it makes more sense for it to be A, where P is the proportion for whom garlic is more effective, than for C. But in other situations, you could almost flip a coin between which way you want to measure that. Anyway, so A is a slightly better choice than C, but they're both the right kinds of things. B is backwards. B is mixing up the idea of a variable with the idea of a parameter. All right. So when we're doing our hypothesis test, if we're trying to decide if one thing is more effective than the other, what we want to do is think about what would it mean for there to be no effect. If there's no effect at all of garlic, then that would mean that there would just be, if you gave someone garlic or gave someone a placebo, there would be a 50-50 chance that it would help. It would be the same probability that it would help. So that's why we think of P equals 0.5 as being the statement that there's no difference between garlic and the placebo. And so that'll be our null hypothesis. So the null hypothesis is very often the measurement of no effect or no association, something along those lines. So that's not an unusual, not an unusual thing to happen. So in this case, the null hypothesis, which is the H0, should be P is equal to 0.5. And honestly, and there's only 3 of those that do that. The null hypothesis for proportions will never be anything other than P is equal to a number. So all these ones that say P less than or P not equal to, those can't possibly be right. So B, E, and F are the only ones that say P is equal to 0.5. There's no, if we're doing a scientific experiment, we don't want to have the bias of thinking for some reason that we know whether garlic is better or worse. So our alternative hypothesis, our safest alternative hypothesis, is always just not equal to. So what we're looking in the problem for is to see if there's any language there that says that the people doing the study believe or want to test something like P greater than 0.5, but there's nothing in the language here that suggests that they want to do something otherwise. So our default alternative hypothesis is just not equal to. Sample size guidelines, that's the same as they are for confidence intervals. We want to, we generally want to have the confidence that, well, first of all, the sample has to be random, and there's an expectation of at least 15 success and 15 failure. So in other words, we need to have enough so that we expect there to be at least 15 answers that the garlic was more successful and 15 answers that the placebo was more effective. So we have that. We don't have much more than that. Notice the sample size here isn't very big, but we do have that. Okay, and so now we get into the hypothesis testing part, and I'm going to draw the picture over here just because I want to continue to work on the logic of this as we go through. You know, obviously you don't have to keep drawing these pictures over and over again, but our picture that goes with this is the hypothetical picture. If that would be the case if H0 is true. So if H0 is true, then the p-hat distribution, the sample distribution, should be centered at 0.5, right? Because that's what H0 says. So when I say assuming H0 is true, I mean assuming the middle of this thing is at 0.5. The standard distribution, the standard deviation is going to go 1, 2. I'm going to have 1, 2, 3 standard deviations in each direction, and that standard deviation of this picture is what we call standard error. And that is the thing that, what was the sample size, 87, I think? Yeah. So we can do this calculation. Hang on a second, I'll do it. All right, so I'm getting, and I'll give myself good 3 or 4 decimal places, 0.0536. As my standard error. So that's how far each of these tick marks are. This is 0.0536 above the middle. This is another 0.0536, another 0.0536, and then the same thing down this way. So that's what that means. And notice all of this is free of the data. Like I should be able to draw all of this before looking at the data. And that will keep you from accidentally using p-hats and other things that aren't supposed to be in here yet. So we draw this hypothetical p-hat distribution based on the null hypothesis, and it's all labeled, it's all good to go. And now we go over to our data. Our data allows us to calculate a sample proportion. So p-hat is 54 out of 87. And that is 0.6207. Again, I'm giving myself a couple of extra decimal places every time. So that's my p-hat value. So what I'm supposed to be visualizing is that p-hat value is somewhere on this distribution. This is a distribution that's supposed to reflect all the p-hats you would ever get if you go off asking 87 people at a time. And so 0.6207 is right around here. It's pretty far up here. And so what I'm supposed to be measuring is how likely is it to get a measurement like 0.6207 on this distribution. And I can see it's fairly rare. It's pretty far out here. So we'll see if we can measure just how rare it is. So the 2 ways that I'm measuring its rareness is, first of all, I'm calculating its z-score. That's what they're calling the test statistic. So this is a number that we can evaluate for how weird it is, see how extreme it is. But this calculation is exactly the same as it has been, as long as we remember that we're measuring things relative to that distribution on the right. So the observation is 0.6207. On the distribution of the right, the mean was 0.5, and the standard deviation was 0.536. And so that gives me a z-score of 2 decimal places? So 2.25. And that's the value that's going to go in the box there. So that goes there. So relative to my picture on the right, this is telling me that this p-hat value I have is 2.25 standard deviations to the right of the middle on this graph. And so that tells me that that value is right there on my graph. And so the next question is going to be, what's the probability that you would get something like that? And so that's where I need to be able to look up things in my table. And that's the main reason that we converted to z-score here, is because our table is in terms of z-scores. So if I erase this. So if I redraw this standard, this normal distribution problem or curve, I really have a hard time with the symmetry, don't I? But I write it in terms of z-score. Z-score would be 0, 1, 2, 3, 0, 1, 2, 3. So 2.25 is right there. And so my p-value, which is my probability of getting an observation that's that far away, would be found by drawing the z-score I have, 2.25, its counterpart on the other side, negative 2.25, and then trying to figure out how much area is in these two pieces, these two tails. The reason I'm using both tails is because, remember, my alternative hypothesis was just that p hat is not equal to, that p is not equal to 0.5, which means I'm not biased towards things being to the left or things being to the right. So if I want to know the probability of being that far away, I have to consider that far away in either direction. So of course our table, it doesn't give us pictures like that, but our table does give us pictures like this. Right? If I look up negative 2.25 in the table, and I'm looking up the negative value, because when I use the negative value, it looks just like the picture that the table gives us. So if I look up negative 2.25 in the table, I'm told that the area under that curve is, hang on, 2 point, I see, sorry, I have a hard time looking at my screen and this, 0.0, one, 2, 2 is what I see in the table. So I'm looking for the z of negative 2.25, and the area I see is 0.0122. So that's the amount of area that is over here, which means that that's also the amount of area that's over here. And so the probability of getting a p hat that's that, well, I'll say it in terms of z, of getting a z that far away from 0 and I should say at least that far away from 0, is just the sum of those two areas, so 0.0244. So 0.0244 is the probability that if you got a random observation, that observation's z-score would be at least 2.25 standard deviations away from the mean in either direction. And the reason that we're saying either direction is because our alternative hypothesis was that p is not equal to 0.5, which means that the alternative hypothesis was not biased towards the p being greater than or less than something. It was simply not equal to. So when we have the alternative hypothesis of the form p not equal to the number, then we always are going to use both areas and add them together to get this probability. And that probability has the name p-value. That's what p-value means. It's the probability that you would have an observation whose z-score is at least that far away from the middle, from 0. So that'll be my z-score is 2.25 and my p-value is 0.0244. they only want 2 decimal places, so we'll leave it at 0.02. Before I say that, the conclusion here then is that notice that we are testing the next part of the problem, which is not included on here, was to give the conclusion if we were testing at the testing at 0.05 significance level. And remember, that's the alpha in these problems. If we're testing at the 0.5 significance level, then 0.02 is small. That's a very rare thing to see. So we would say, since the p-value is less than the significance level, so that is 0.02 is less than 0.05, then we reject the null hypothesis. So in other words, we believe that the picture that we drew originally is not right. That picture can't be right if we were able to collect something the way that we did. So like I was saying in class, the issue is here that you're collecting real data and then comparing it to a hypothetical picture. And so when that happens, then you're saying that you don't believe the hypothetical picture. So our statistics-free conclusion would be then that we have enough evidence to support the claim that, and in the language of the P that we came up with, it would be, I'll put in parentheses here, that P is not 0.5, right? So it's the alternative hypothesis that we're writing here. But rather than say P not equal to 0.5, which is really hard to say, really hard to think about, we want to say that, we support the claim that garlic does have an effect on, and now I've forgotten what we were even testing. Was it blood pressure? I don't know. I forgot what the question was now. But we're saying garlic does have an effect. So remember, that's what P not equal to 0.5 means. P being equal to 0.5 means that there's no difference between garlic and a placebo. So P not equal to 0.5 means garlic has an effect. Notice that we're not saying that garlic has a good effect or a bad effect, just that the garlic people definitely have a different value than the placebo people. Okay, so then briefly in StatCrunch, if you wanted to do the same problem. So just real quick, I should say here, under the stat menu, so under stat, if you go proportion stats, one sample with summary, this is the same thing that we did for the confidence intervals. You come to a screen that looks like this. So we're going to tell it that we're going to do a hypothesis test for P. We have to tell it the hypotheses that we're using so that will match what we did before. So P equal 0.5, alternative is P not equal to 0.5. And all the rest of this does not matter. But then up here, number of successes, number of failures. So this is relative to this P proportion. P, remember, was the proportion of people who were helped by garlic or had better whatever with garlic. And so 54 out of 87 observations was where we got our P hat from. So that's what's going in here. This is the P hat calculation, number of successes, number of observations. So that divided by that would be your P hat. Anyway, so once we have that information, then we can just hit compute down here. We get the outcome of all of this stuff, and you can see that not only does it tell me my P hat value here, that is what I got, 0.6207. It's telling me my z-score here. It's telling me the p-value here. That's what I had. It even throws in standard error. We didn't. They didn't ask us that in the problem, but we had to calculate that, right? We had to calculate standard error in order to do z-score. So there are all the calculations that we did that it just does automatically for us. And so then in the problem, it asks you to to interpret what we have. And I think that's kind of what we wrote down, but let's just make sure I'll pick the right one. The p-value is less than the significance level, so it's it's A or B. And when the p-value is less than the significance level, we reject the null hypothesis and say there's sufficient evidence to support the HA. That's what we're trying to say. There is sufficient evidence that, and then whatever HA says. So not this one either. This says there's not sufficient evidence. And so this last statement is them trying to put into words what the HA is. The proportion of people who found garlic more effective is greater than 0.5. That's not really what we found. We really found just that the proportion who found garlic more effective is not 0.5. Remember, that was our alternative hypothesis. So I think they've lost track of that a little bit here, but that is the best of the options that they give us is A.